Hello students, you all are welcome to the program here doing a chemistry lesson regarding the very first unit that you find in A-level chemistry syllabus. So we are going to talk about the Bohr's structure here, Bohr's model regarding the atom here in this. So when we check for the content here in this lesson that you have, it covers the competency 1 and it is 1.3, the competency level. So it is uses electronic arrangements and energy transactions in determining the nature of matter is the competency we have there. But the competency level there states evidences for electronic energy levels of atoms. Students, the content, if I explain on you, you would find variations of successive ionization energies of various elements, introduction to Bohr's theory and Bohr's model, atomic spectrum of hydrogen, its explanation of hydrogen spectrum using Bohr's theory, quantization of energy, existence of electrons in energy levels. Those are the facts we have got there in this lesson. So, students, we are going to talk about the Bohr's model. What's Bohr's model? Students, Bohr talks about the model of an atom. It's after revealing of those subatomic particles, electrons, protons, neutrons. They seek for a suitable structure standing for an atom. Students, you could find in their evolutionary stages 4 models presented standing for an atom. Amongst them, it's the very first you could find the plum pudding model of J.J. Thomson. So, Thomson said an atom is like a plum pudding. Electrons are immersed. They are within a positively charged globe with cations. It's protons. So, students, it's what J.J. Thomson said. So, then after, it was Ernest Rutherford, after revealing of the nucleus of an atom using his gold foil experiment. So, Ernest Rutherford revealed that you have a nucleus there consisting protons and neutrons there in it. All electrons are orbiting around the nucleus as all the planets are orbiting around the sun. Okay, that was the planetary model. So after those 2 models, it was Bohr's model presented for the reason there were some limitations stood there in earlier models. So students, Bohr's model was successful. It was quite successful than other 2 models for the reason it could nicely explain about the successive ionization energies of those elements, various elements, as well as atomic spectrum of hydrogen. That's what we are going to talk here about. Students, in his theory, Bohr stated a hypothesis. Actually, we could call it a postulation. What's the postulation Niels Bohr presented? Students, Niels Bohr in his theory he talked about something called energy levels. Till then, there was no such word as energy levels, others knew. So it was for the very first time Niels Bohr presented this idea about energy levels, saying there are raw energy levels around the nucleus you get. So energies of energy levels are constant. So when it goes away from the nucleus, the energies of these energy levels get increased, while the gaps between those energy levels get decreased. That's what you get there in Bohr's model. Further, he stated that you could find electrons there filling inside those energy levels. So, those electrons get filled inside energy levels, inside atom, in the increasing order of their energies in energy levels. Presenting that, Niels Bohr showed something like you have energy levels there in an atom. So he showed that you get first energy level, second energy level, third, fourth, fifth, sixth, like that. So it continues like to the infinity. So students, next, it's at the beginning those were named as K, L, M, N, O, P, Q, R, S, T, those like. But later on those were named as numbers as quantum levels. So it's we call it first quantum level, second, third, fourth, fifth, such quantum levels you get. So students, further, what are the advancements or advantages we could pick there up from Bohr's model? Students, you could talk about Bohr's model as it explains the reasons for large deviations having their standing for successive ionization energies of elements, as well as it explains nicely the atomic spectrum of what? Hydrogen. Students, we are going to first talk about the successive ionization energies. So, successive ionization energies. What would you understand by successive ionization energies? Students, before talking about successive ionization energies, let's find it out the concept what is this ionization energy stands for. Okay, ionization energy, ionization stands for removal of electrons. When you remove electrons, we call it ionization. So, the energy it requires to remove electrons from an atom is the ionization energy. But though we talk about one atom, it's a very low energy amount you would require there standing for one atom. Therefore, students, it's not we are going to talk about just one atom only. We are going to talk about a bunch of atoms. How many? It's a 1 mole of atoms that we are going to talk there about. So students, then we could remove the first electron out there and you would get then unipositive ion. Then you could remove another electron. Then it is a dipositive ion. So accordingly, you could remove one by one all those electrons. So when you talk about the removal of first electron, it's the first ionization energy. Okay, let's talk about the first ionization energy. Students, it's a must that you need to take those atoms at gaseous state. Otherwise, the energy you supply could be used for other purposes as state transformations. So, you need to avoid that having. Therefore, students, let's talk about atoms at gaseous state. It is the minimum energy that requires to remove 1 mole of electron. 1 mole of electrons from 1 mole of gaseous atoms as to form 1 mole of unipositive cations. The energy required to do that is the first ionization energy. So students, various elements would have various first ionization energy values. Okay, let's talk about the second ionization energy. Students, when we go to the second ionization energy, it is after removal of one electron already, now we are going to remove the next electron. Students, when you talk about the second ionization energy, it's the minimum energy amount it requires to lose another mole of electrons from 1 mole of unipositive ion as to form 1 mole of dipositive ion. So, it's what we call the second ionization energy there. Students, let's go to we could go to the third, fourth, fifth as next ionization energies. Accordingly, you could remove many electrons, but it has to be the number of electrons it is having. Otherwise, you can't remove more than electrons it's having, right? Okay. So, students, you could remove nth electron as well. So, we talk about the nth ionization energy there. Students, when you talk about the nth ionization energy, it's the minimum energy that requires to remove another 1 mole of electrons as to form N plus cation. N plus cations at gaseous state. You need to make that sure it has to be at gaseous state. Okay students, when we talk about nth ionization energy, it could be you are removing 1 mole of electron. Make sure that it's still 1 mole of electrons. So, you are removing. So, it has to be from gaseous ions, but these gaseous ions now you need to have at as it is n minus 1 plus the charge of it. So, it's you need to remove 1 mole of electron from its, if it is sodium, let's take it as the example, if it is sodium we talk about, it is losing of 1 mole of electron from n minus 1 positive ions as to form sodium n plus gaseous ions. So, the energy it requires to do this is what we call the nth ionization energy. Okay. Likewise, we could talk about the successive ionization energies. Students, anyway, it's removal of electrons. Removal of electrons need energy. So, always it's going to take energy. But it's going to get increased all the times. It's you don't need any such model to explain that. It's you could understand, hope you could understand that fact. You have equal number of electrons and protons within an atom if the atom exists at its neutral condition. So, students, after removal of 1 electron, anyway removal of 1 electron also would be quite difficult, but after removal of 1 electron, next electron would be attracted by same number of protons earlier was. Let us say it's sodium. After losing of 1 electron from sodium, it's next you have 10 electrons being there. But 11 protons still, make that sure that you have 11 protons still. So, those 11 protons they are attract still all 10 electrons. Therefore, the effort you need to put there would be greater than of earlier. Students, therefore, it's very clear that next and next, then after next one, it would take more energy than of earlier it took. So, therefore, it's obvious that you could expect an increase of energies standing for those successive ionization energies. But the thing is, when we talk about those sodium's successive ionization, as it was the example we took earlier as well. So, we could find it out that sodium's first ionization energy, second, third, fourth, fifth, like this. Look at these values. These values, when you check, values are increasing. For sometimes you could find large increments. You could find out large increments there between some consecutive ionization energies. So, then when you check for the others as well, you could lose all the 11 electrons that you find inside sodium. So, you could find out 11 ionization energies. Altogether, we call the successive ionization energies of sodium. Students, if I represent those in a graph, you could find it being like this. So, students, check this. If you take real values to the y-axis, values of those ionization energies to the y-axis, you could easily find it out, it's climbing very up. So, to avoid that having, let's take their log values only. Let's take their logarithm values of those ionization energies there. So, then we could have a graph like this, having this shape. When you analyze this graph, you could find it out here as well as here, having significant increments of their ionization energies. So, the reason, why is that? Why is that they are having a significant increment there between first and second ionization energies, as well as they are between 9th and 10th ionization energies? Can you explain that using just the idea that you have protons and electrons there only? No, you need this model, Bohr's model. So, Bohr's model could easily explain that the reason for having such kind of large increments. Okay, so now our effort is to analyze that using Bohr's model. Okay, students, Let's find it out. How is that you could have such large increments having between some ionizations, consecutive ionizations only. So with others, you could find it's not that smooth, but it's quite smooth slope you are having. So when we try to explain that, we need the support of Bohr's model. Okay, students, according to Bohr's model, you have energy levels. Let me show that. If we take the nucleus here, okay, so you would have the first energy level there. It's for the easy understanding, I'm going to draw the next energy level. It's not the second. It's the last energy level I'm going to take now. Students, I will explain why is that I'm telling that. Students, it's taking the last energy level at the next time after drawing the first energy level. It's let's find it out the difference between or gap between first and last energy levels, and let's divide it by 2. Let's take a half distance there. So taking a half distance there of first and last energy level, and if it is here around, if you take bit away from that, so you could find the second energy level. So it explains everything. It explains that you won't ever get the same gap again after second energy level. Second to last, the gap you find is less than of the first to second gap. That's what it reveals. Okay, student, shall we draw the third energy level? Okay, when you try it out, drawing third energy level, you again get a half distance of that. Then bit beyond that, you have the third energy level. So let me show that this is the third energy level. So accordingly, we could draw those energy levels that you have, they are within an atom. So having those energy levels, let's fill those with electrons. How would energy levels be filled with electrons? When you fill first shell could have maximally 2 electrons. Okay, when it is the second shell, students, what is the maximum number of electrons you could ever fill in a second shell? It's 8. It's 8 amount of electrons you could fill there in the second shell, inside second shell. What about third shell? Is that still 8? Okay, under the circumstance, if it's the last shell, yes, it is 8, the maximum number you could fill. But students, if it is not the last shell, if you have further shells being filled, let's say after 29th, the atomic number, the third shell would be having maximally 18 number of electrons. So accordingly, it's possible 8 electrons, 18. Also, when it exceeds the atomic number, it's possible, when it exceeds the atomic number 70, it's possible fourth shell to be filled with 32 electrons as well. Okay. So students, in sodium, there would be electrons filled in a manner like 2 in the first shell, 8 in the second shell, and 1 in the last third shell. Okay, this is what Bohr explained. Bohr explained that when you take sodium, as I have already explained, you have 11 electrons. So those 11 electrons would be filled as 2, 8 and 1. So students, if we take this as the last outermost shell, so what is the ionization there? What is the first ionization there? So when you give energy, this electron in the third shell, outermost shell, would get excited to upper levels. So the last upper level it could ever get excited is the third level, nth level. It's the nth level. So it would get excited to nth level. So then if you give furthermore energy, what would happen? When you give furthermore energy, this electron would jump over the atom. That's the first ionization energy you get there. Students, when you give energy more than of this, it would jump over the atom. So you get the first ionization energy. Okay. Students, when you are about to remove the next electron, what would happen? Next electron, you can't find that in third shell. Next electron is there in the second shell. So it's you then need to give energy on an electron that you find on second shell. So students, then it's you need to give at least this much of energy. That represents the gap between second and last shell. So when you give furthermore energy between second and last shell, that gap, so when you give furthermore energy than of that, it would escape, it would jump over the atom. That's the energy it requires. So that's the second ionization energy. So hope you could still remember that we saw that between first and second energy levels, that you have got there what? You have got there a large increment. That's the reason for the large increment you have here. So students, if I go back, I could show that the next 8 electrons you have there in the second shell. So then it would be you are removing electrons from the second shell still. So after removal of all electrons, including this 8, it is 9. So after removal of 9 electrons, what would happen the next energy it requires? It would require energy to remove 1 electron from this. Okay. So students, that's the 10th ionization energy. So that's the 10th ionization energy having this big gap there. So students, you could find this difference getting add there to the next means 10th ionization energy. If I show it again in this, it's the gap here you get. Okay, hope it's clear. It's Niels Bohr, using his model, could nicely explain how is that. You are having those big gaps there within the successive ionization energy patterns there. But students, Bohr also was unable to explain these slight increments, the reasons for the slight increments that you could find there around. So then it's using the concept existence of sub-energy levels, you could reach that. Anyway, Bohr could nicely explain how is that you get large increments there within successive ionization energies. Okay. Then shall we talk about the hydrogen spectrum? Okay. So students, as I have first stated that fact, Bohr's model was successful in explaining the reasons for large gaps between those successive ionization energies, as well as Bohr could nicely explain the absorption emission spectra of hydrogen. Okay, let's take a look at what these absorption emission spectra of hydrogens first. Okay, students, when we talk about absorption emission spectra of hydrogen, it's first we need to talk about the concept called spectrum. So, electromagnetic spectrum. What is an electromagnetic spectrum? Students, when you get electromagnetic waves there, it's when you arrange them, all the possible electromagnetic waves in the increasing order or decreasing order, ascending or descending orders of their frequencies or wavelengths, it doesn't matter. So, if you find all the possible waves they are being found, it's called a continuous spectrum. So, you have various types of those electromagnetic waves. Let's talk about them. Students, you could start from radio waves, the least energy. Then microwaves, you have IR, infrared, visible light, UV, X-rays, gamma rays, even cosmic rays. So, it's various such electromagnetic waves you would get. So, among them, when you talk about those visible light, student, visible light is not having one type of waves only. It's many waves you could find with many frequencies. So, all those different frequencies, each frequency would have its own color, own inherited color. So, it was first revealed by Sir Isaac Newton. It was first revealed by Sir Isaac Newton there. So, passing a beam of white light through a prism, so he showed that you get rainbow colors there. Students, that's what we call the continuous spectrum. It is when you pass white light through a glass prism, you could differentiate those into their component frequencies, colors. So, you get these rainbow colors there. So, it's VIBGYOR from this end to this end you get. It is VIBGYOR, VIBGYOR. So, students, you get 7 colors there. Violet, indigo, blue, green, yellow, orange, red are the 7 colors you get. Though you call them 7 different colors, you have sub-colors within those each colors. It's not just one color only you get there in VIBGYOR, in those rainbow colors. So, when you have all the possible colors being found there within a given set of those such set of colors, we call a continuous spectrum. Students, it's the continuous spectrum that you get when you pass white light through a glass prism. So, why is that we talk about the continuous spectrum here? Our purpose is to explain you about the absorption spectrum and the emission spectrum of hydrogen. You would get absorption emission spectra for other elements as well. But students, I need to emphasize this fact. Niels Bohr, using his model, could explain only about hydrogen's absorption emission spectra. It's not about those other elements he could explain. The reason, he did not have a proper idea regarding the behavior of multiple electronic systems. Anyway, he was successful at least in explaining this hydrogen's absorption emission spectra. So, therefore, we need to honor the person. Anyway, let's go back. So, students, when you have those rainbow colors, you might have seen enough those rainbows there when it is raining out there. Okay. So, students, it's the continuous spectrum when you have those rainbow colors. We call that the continuous spectrum. So, any white light source could provide you that rainbow color set. You could find them out passing those through a prism. Students, when we talk about the hydrogen's absorption spectrum, you need to pass white light first through a sample of hydrogen gas. Students, when you expose hydrogen to white light, then when you get the transmittance energy, transmittance light, then when you analyze those transmittance light after passing through a prism, so those would get differentiate as into those colors, component colors there. So, among those colors, when you check whether all the colors are still there, you could find out some colors are being missing, some colors are absent. Why is that? Just some colors are not there. So, students, it's just for the reason those colors being absent were being absorbed by the sample of hydrogen. How could it be possible? It could nicely be explained using the Bohr's model, Bohr's structure regarding the atom. So, that's the hydrogen's absorption spectrum. Again, when you pass white light, a beam of white light through a hydrogen gas sample, when you check for the resultant light, passing through a prism, you could find some dark colored lines they are appearing in a colored background. Those are dark colored lines, few lines you get in a colored background. So it's called the spectrum, the absorption spectrum. It's after being absorbed. So it's the absorption spectrum of hydrogen. When you check for the property of this absorption spectrum, students, you could find in the increasing direction of their frequencies of those waves. It's the gaps between those consecutive lines are getting decreased. It's such a pattern you could observe there when you check for the absorption spectrum of hydrogen. Students, then let's talk about the emission spectrum of hydrogen. You once give a chance to hydrogen as to emit, as to express itself, as to emit energy radiation. How you could do that? You make it excite. You just excite someone and see what that fellow is saying. That's the excitation, that's the motivation. So students, similarly, it's when you excite, when you motivate a sample of hydrogen there, you could see that its performance of that hydrogen sample. What performance? This hydrogen sample then after would start emitting what? Radiations. So that light, the light that it emits after excitation of the sample of hydrogen. How could you do that? How could you excite a sample of hydrogen saying, hydrogen, you are very good? No, it's not the way. You supply a high voltage difference there. That's the way. So you could do that on students saying you are very good. But on hydrogen, you need to provide just energy. You provide energy. You provide energy and see what it happens. Students, when you provide energy on a sample of hydrogen, the atoms within the hydrogen sample would get excited. After that excitation, it would start showing its performance. It would start giving out what? Light. When you analyze that light, it's giving out. How would you analyze? You could simply pass that light through a prism, as here you have. So this is hot gas, means excited sample of hydrogen. So you could provide high voltage difference here, so as to excite them. So then this hydrogen sample would start emitting light. Then how would you get this beam only? You could cover this hydrogen bulb. Let's call it a bulb now. You could cover this hydrogen bulb with a what? Opaque barrier. So simply you could use a cardboard there. Okay. Students, you make a slit there. Then through that slit, it would give out a beam, fine beam of that light emitted by hydrogen. Okay. So what you need to do next is you pass that through the prism that we earlier used. Okay, and see what it happens. So at the beginning you would find that nothing having there. But when you check carefully, you could find out here, there. So some colored lines are appearing. Students, within a dark background, you are having few colored lines. These few colored lines that you are having there within that dark background is the emission of hydrogen, is what it emits out. We call it the emission spectrum. You don't be scared. It's the emission spectrum of hydrogen. Students, it's these few colored lines that you find within a dark background called the emission spectrum of hydrogen. So those are the two spectra. So the plural of spectrum is spectra. So students, when you check for the similarity between them, those two spectra there, it's you could find out the line belong to this, the line here you get is filling this absence. Those lines or those frequencies were absent here, absent there in the absorption spectrum due to the absorption of those frequencies are coming here. Those who were absent on that day are coming today. All those who were coming on that day are absent today. So, it's you add them up, then you could fill whole class. Means it's you could fill all the whole set of those electromagnetic radiations. It's what you get there is the all are coming on that day. So, it's the continuous spectrum. It's the continuous spectrum. It's this what you get. So, students having a close look, making a close look at these two, seeing the pattern of those lines. So, it was scientist named J. Balmer explained that always, though it is the emission spectrum or absorption spectrum of hydrogen, the pattern is the same. Whatever the spectrum you get there, the pattern you have is the same. It's the same pattern. So, it's this pattern. You have here a line, here a line, here a line, here a line. A pattern like this. It is within the visible region. Within the visible region, you get such a pattern. So, students, this pattern was revealed for the first time by the scientist as I named J. Balmer. Therefore, to honor him, we call this pattern, this line spectrum as the Balmer series. Students, it's the Balmer series. It's the Balmer series. It's appearing there, it's you could have there within the visible range. It's within the visible range. Okay. Then there were some other scientists curious at what Balmer found out. So, Balmer just showed that there is a pattern of those spectra. So, having there standing for emission, absorption spectra. So, another scientist named T. Lyman thought that I better check whether a similar spectral line series is given within the UV region. So, he did that and he was successful. So, he got the luck. Okay. So, he could reveal that there is a similar spectral line series that you could find within the UV region as well. So, this is the UV region. UV is ultraviolet. So, within the UV region, such a spectral line series was revealed by the scientist named T. Lyman. Students, this series, spectral line series is identified as the Lyman series. Lyman series. So, when you compare this spectral line series, it's quite similar to this spectral line series, but the gaps here is quite larger than of this. Students, it's quite like this is the big version of this. This is the Balmer series. So, Lyman was lucky enough to obtain such a series what we identify as the Lyman series. There was another scientist thought in the same way. So, students, his name was Parshan. Parshan was thinking, okay, Balmer found a series there within the visible region. Lyman tried it there within UV region and found. Why shouldn't I try it within IR region? Thinking that, Parshan, scientist named Parshan, also worked on it and revealed another series there. So, another series there behind the visible region, behind mean it is lesser in frequency, means energy than the visible light. So, he revealed another series there within IR region. So, it also was quite similar to that series, Balmer series, but now the gaps were quite smaller than of Balmer series. We identify this series as the Paschen series. Students, in that manner, those three scientists, Lyman, Balmer, Paschen, revealed Lyman-Balmer-Paschen series. So, the common thing regarding all these spectral lines that in the increasing direction of their frequencies, the gaps between consecutive lines are decreasing. It's what you get when you compare all the spectral line series together. There were another two scientists, we don't talk much about them, but another two scientists named Brackett and Fun also further revealed another two series they are behind the Paschen series in long IR region. So, we call them as Brackett series and Fun series. Okay. Students, do you know what's the reason for having of these spectral lines? We could use Bohr structure, Bohr theory to explain the reason for having of these spectral lines. Niels Bohr could nicely explain the reason for having of these spectral lines. Let's find that out. Okay, students, when you check for the absorption spectrum of hydrogen, you could find some dark lines being there within a colored background. When we start explaining that using Bohr's model, I would use these as first, second, third, fourth and nth energy levels. So, I will draw them in the direction that in the direction that their energies get increased, like first, second, third, fourth and last. So, I am going to show you their electron transitions having during that absorptions. So, students, it's the visible region. You get these dark lines. When you get dark lines within the visible region, they absorb visible light, frequencies from visible light. Let's talk about how is that the absorption spectrum of hydrogen evolves. A hydrogen atom is having its first electron there in its very first shell. Look at this. You have the electron here on the first shell now. So, students, then after this electron, after given energy, it would excite on the second shell. So, after being excited there to the second shell, then you have the electron on the second shell. So, when we start explaining our story regarding absorption spectrum of hydrogen, we need to start it with the electron at the second shell. Students, the electron at the second shell would absorb energy, as to excite. This is the first shell. So, you have got electron. So, it's for the here I am showing that excitation that I have already explained. So, now you have the electron on the second shell. So, we are ready again. Students, the electron on the second shell would get excited to the third shell. So, it would jump to the third shell after absorbing enough energy. This energy you could find within the visible region. Within the visible region, you could find this energy. So, that hydrogen atom having got its electron on the second shell would absorb energy as to jump to the third shell. So, that energy is being absorbed, therefore, that energy is missing in the resultant set. So, that is why you get a dark line there within a colored background. Students, I could show it here in this diagram in this manner. So, electron on the second shell would excite to the third shell, absorbing energy. It would be absorbed from the visible region. Energy would gain energy from visible region. So, that particular frequency would be not there in the resultant. So, that is the first line. of the absorption spectrum given. Students, when you go back, it's again we are ready having our electron on the second shell. I am not saying that all the electrons were there on the second shell got excited to the third shell only. It's some of them, it's just a fraction, just some amount only of them made that excitation. Still we have some further hydrogen atoms willing to get excited. When they find suitable energy, they won't absorb energy like that. They won't absorb energy like that for the reason it's useless. There is no place to excite there. Therefore, Bohr nicely explained that you have fixed gaps only. They are between energy levels. Therefore, only some particular frequencies are absorbed. So, hope you know this fact that E equals HF. So, the energy, if that energy is given by electromagnetic radiation, that electromagnetic radiation would be having a particular frequency. Therefore, to do one excitation, it always would need some fixed amount of energy only. Therefore, always that electron would be absorbing that particular frequency only. That is why it is a constant line you get at all the times. Students, if we extend the story, so another electron on the second shell would get excited to the fourth shell. So, it would absorb some energy. That energy would be there given by a particular frequency. That frequency would be missing here when you provide all the frequencies with the white light, whole set of frequencies, those frequencies being absorbed are no longer there, you could find. So, therefore, another dark line you could see there for the reason that frequency was being absorbed. So, students, I could show it in this diagram. So, it's from second to fourth, the electron would get excited, absorbing energy. So, then that frequency would be missing there in the transmittance, in the resultant. So, that's the reason for having another line there. So, this gap between first and second lines. So, that gap is represented by the gap here, the gap between third and fourth energy levels. For the reason, students, you again imagine the excitation made by the electron on the second level to third level and second level to fourth level. The difference of energy there is the difference of third and fourth levels. Therefore, that difference of energy is represented by the gap between these two lines. Then let us talk about another excitation. When you talk about another excitation made from second to fifth level, it would further absorb energy, a greater energy this time. So, then would make that excitation. So, if I draw the fifth level here, it would make that excitation from second to fifth level. It would further absorb a greater energy. That greater energy would be greater than of earlier with this amount. Therefore, its gap now is quite less between next two lines. So, in the increasing direction of their frequencies, students, you could find the gaps between consecutive line getting decreased. So, those gaps represent their difference in energy between those consecutive energy levels. Okay, that's the reason for having those absorption spectral line series. Then let us go to emission spectral line series. Okay, when you talk about the emission spectral line series, it's those colored lines earlier was being absorbed, now are emitting by hydrogen. It's for the reason, students, after given of energy, the electron on the first shell of hydrogen would get excited to upper levels. Then those electrons would arrive back to earlier levels, lower levels, for the reason being at upper levels they are unstable in energy. So when they arrive back to the second level, they emit energy representing those colored lines or colored frequencies. Okay, then you get the emission spectral line. So if I explain using this energy level diagram, so an electron on the third shell would arrive back to the second shell emitting energy. So that energy it emits, if I show it in with this line, so students, next you would have an electron on the fourth shell. So that would arrive back to the second shell emitting further energy. That energy would be greater than of earlier, it's greater than of earlier with this amount, with the difference of third and fourth shell. So you get greater energy than of earlier. When it's arriving from the fifth shell to the second shell, it would be further greater energy emitting, but now the difference is given by the difference between fifth and fourth energy levels. That difference is quite small, therefore you find the gap between next two lines being smaller than of earlier. So it continuously getting small the gap between consecutive lines. In the increasing direction of energy means the increase in direction of their frequencies. That's how we could easily understand how this emission spectral line series is given. Students, it's T Lyman found out Lyman series, Balmer series. So these emission absorption spectra of hydrogen is the Balmer series, representing Balmer series. Then how could I explain having of Lyman and Paschen and other series? Okay, then we are now going to find out how those spectral line series given for Lyman and Paschen as well. Okay, let's find that out. Okay students, hope you could remember this spectral line series having Lyman, Balmer, Paschen, those spectral lines. So if I start explaining how those spectral lines are given, when you find, let's talk about the emission spectral lines. When you find excited electrons arriving there to the first shell. So when those excited electrons already on upper levels are arriving back to the first shell, they would be emitting energies. But they all would be having this difference of energy between first and second. That difference is a huge difference. That does not belong to the visible light region. So that belongs to the UV region. That's why for those arrival, they are emitting energy within the UV region. So students, you could find that these Lyman series spectral line series being given by the emission of energy when electrons are arriving from upper levels to the first level. Similarly, as we have already found that out, the fact the Balmer series you could find out within the visible region. It is given by arrival of electrons from upper levels to the second level. Then you could find visible light frequencies emitting there. So students, that's what you get, that's how you get the Balmer series. Okay, when you talk about the Paschen series, do you know how Paschen series evolve? Students, it's the arrival of electrons from upper levels to third level, they emit energy. So they emit energy belongs to IR region. That's why you get a spectral line series there within the IR region here. Okay, in that manner, we could explain having of Lyman, Balmer, Paschen series there. Okay students, these are few simple things that you could use Bohr's model to explain them easily. Hope you could understand these few simple things that you find in the first unit of chemistry. Student, this subject chemistry is very simple when you go through that in a logical way. When you understand those points, and you don't need to by heart these. If you understand them, you could easily go through these. These are easy points that you find there out. Students, therefore, I could name this subject chemistry as the easiest out of those others. Okay, we are going to round up here in this program, in this lesson, willing to meet you again in our next lesson. Okay students, goodbye.